Swayam Prabha. Digital India. Educated India.
So, let us continue with the concept of entropy that we have started working upon, all right. So, last time, last time we saw we saw that there is we are still so this entropy that we actually kind of accidentally discovered from Carnot cycle, which was the ratio of heat to temperature. So, last time we thought okay, there must be a simple way to understand the concept of this entropy, and therefore, we introduced the concept of microstates and macrostates, right. And microstate is like all the accessible coordinates in terms of position and momenta of the gas molecules, which correspond to a typical value or certain value of a thermodynamic variable, right. And we said that thermodynamic variable is a macrostate, and there can be multiple microstates associated with that macrostate, right. And we saw we basically derived what is known as Boltzmann equation of entropy, and we saw that this entropy S can be written as Boltzmann constant times log of a quantity omega, where omega is the number of accessible microstates. Corresponding to a particular macrostate, all right. And later on we also defined another way to represent this entropy, and the way we posed the question was, what if the macrostates can also switch between different, so the system can switch between different macrostates as well, right. And say there are multiple macrostate and system can switch between those macrostate, in that case that also contributes to the entropy, all right. And if you remember, so the last time we said that say there are certain number of macrostates, okay. So, say so we said that say there is this total number of microstates, which is sum over all the accessible macrostates in the system, and we also said that say there are ni number of microstates in an ith macrostate, right. And then we defined a probability Pi, which is ni divided by n, and this is the probability to for okay. So, for probability for the system to be in ith macrostate, okay. And when we did the calculation, we ended up with what we so we ended up with an expression which looks like this: S equals minus Kb sum of I Pi log Pi, right. And this is basically gives expression for entropy, okay. So, this is where we ended our last class, and we can now quickly see the situation where these two definitions of entropy they merge, they converge with each other, right. So, consider there are sigma number of macrostates and system can switch between all these macro states, and say the system can exist in all of these macro states with equal probability, right. So, in some sense now you can think about it as some kind of a micro state, right, if you think about it, right, like the way we defined our micro states, that system can exist in all the micro states with equal probability. Now we are just calling it, say, system can exist in omega number of macro states with equal probability, right. So, then what will be the probability to exist in one macro state, right. So, the probability to exist in any macro state, okay. So, let us say Pi is equal to 1 divided by omega, and this quantity is same for all the macro states, right. And now we can, what we can do is we can plug this quantity back into the Gibbs expression. So, therefore, we can see S becomes minus Kb, the sum over I 1 by omega log of 1 by omega, and if we sum 1 by omega times, so this just becomes Kb times omega divided by omega log of omega, and I have absorbed the negative sign, and you can see that this just becomes Kb log of omega, right. So, if the system has equal probability to stay in all those macro states, and we just get the expression which is the Boltzmann equation, right, which now tells us that the entropy associated with any macro state with omega number of micro states is given by that expression, right. So, this is how they are related to each other, okay. So, next what we will do is we will actually introduce another concept which is known as Shannon entropy. And this is also known as entropy of information. Okay. So, without going into too many details, I will just give you one example, all right. So, what is information, right. So, let us take an example. So, let us say we flip 3 coins, right. Let us say we are tossing 3 coins. So, flipping of 3 coins, right, and you can, as we know that coin can either have head or a tail, right. So, what are the possible outcomes? So, in one case we can get all the heads, in other case we can get the coin number 1 to be tail, then head. The other possibility is this, right. I am writing down all the possibilities, TTH, THT, HTT and TTT, right. And you can say since every coin has 2, so this is basically equal to 2 number of possibilities raised to the power number of coins, right. This is 8, as you can see this is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible outcomes in this problem, all right. So, there are in some sense 8 number of microstates associated with this. Now, I want to ask a very different question, right. So, let me ask a question. Let us say I want some information out of this experiment, right. So, say I want to know what is the probability to get at least one head, right. Say I toss 3 coins, it will give us different outcomes out of these 8, any of those outcomes. Now, I am asking what is the probability that at least one, so I want that information where I am asking what is the information, the probability associated with the information that at least one coin is head, right. And you can see how many outcomes are possible in that case, right. So, this has a head, this has a head, this has a head, 3, 4, 5, 6, 7, right. So, information, okay, information related to, okay, okay. So, what I am saying is information, okay. So, I want information about at least one coin to get head, right. And you can see this is a small amount of information, right. So, because I only want information about one coin, and you can see in this case the probability associated with this is 7 divided by 8, right. Now say I want more information about this experiment. Now say I want what is the probability to get 2 tails, for example, right, information about getting 2 tails, right. Now I want information about 2 coins, and now you can see the number of ways that is possible, or getting at least 2 tails. So there is 1, 2, 3, 4, right. So there is 4 divided by 8, and what is this number? This is the probability associated to that information, right. And similarly, this is the probability associated with this information. And let us say I want to know what is the probability of getting 2 heads and 1 tail, right. So this has more amount of information, right. So 2 head and 1 tail, and you can see that there are 3 instances in which that is possible, right, and the associated probability is 3 by 8, right. So the point that I am trying to come to is, the more information we want about a system, the lower is the probability of that particular information instance, right. Maybe I can take another example, right. So say I want to get the information of the month in which you are born, right. So there are 12 possible months, right. So the associated probability with that is 1 divided by 12, right. And say now I want to know the month as well as the date of your birthday, right. And now you know, like, there are 365 number of days in the year, and the corresponding probability of that will be 1 divided by 365, right. So the more information I want to gather about certain process, the lower is the entropy, right. So the conclusion of this simple exercise is, more information is always associated with less probability, right. They are kind of inversely proportional to each other. So one goes up, the other goes down, all right. And therefore what we do is, we define a quantity which is known as information content, right. So define information content as follows. So say the information content denoted by symbol Q is minus k log to the base 2 times p, right. So log to the base 2 basically means it is a binary information, right. So for example, a coin can either have a head or a tail, right. So there is a bit associated with it, all right, where p is the associated probability. Okay. And why do we have negative sign? Because we know that probability is always less than 1. So to make this information a positive quantity, we put a negative sign in front, all right. So then what will be the average information content, right. So what will be the average information, and let us denote that by average Q, right, and that is basically the product of probability to have that information multiplied by that information, right. So sum over I Pi times Qi, right. Okay. So and so this basically, if we can just substitute this, so this is I Pi times, so minus k goes out, minus k times Pi log to the base 2 times Pi, right. And you can see that this is similar to the Gibbs expression for entropy as we saw in the last class, but the difference is that here the constant k is not a Boltzmann constant, right. So it does not really have to be a thermodynamic process, right. Tossing a coins is not a thermodynamic process, all right, but still there is an information associated with this, and this is known as Shannon entropy. Okay. So there is certain entropy which is associated with the information, right. And and let us see why this is useful. Okay, and I will very quickly and briefly mention a paradox which is known as Maxwell-Demon paradox. Okay, so Maxwell's Demon, and this is as follows. All right, so about century or 2 centuries ago, so Maxwell basically did a thought experiment, right. So he took a isolated system and he put a wall between two subsystems. Okay, and okay, so that system had, say, some gas molecules. So some gas molecules were red, which were moving faster than, on average moving faster than the blue ones. Okay, than the blue ones. Blue ones represent slower molecules. Okay, so he thought, okay, let us do a thought experiment where I introduce, okay, so where I introduce a wall. All right, so let me draw this again. So where you, and this is insulated. So introduce a wall, okay, and put a daemon here. So daemon here, who can basically allow only the faster moving gas molecules on the right side of the container, whereas on average he will keep the slower gas molecules on the left, right. So every time these gas molecules they come close to this channel, to this opening, so this daemon will actually measure the velocity of that individual molecule. If it is greater than some average quantity, he will let that molecule pass into the other side, but the cold molecules will remain inside, right. So in some sense you can see that this daemon can basically do what is not allowed according to second law of thermodynamics, right. So that is basically what's happening is heat is flowing from, so maybe I can write, so this daemon essentially is doing, he is allowing heat to flow from cold to hot region, right, and this is again like which is against the second law of thermodynamics. So basically to solve this paradox, again like this entropy of information comes in our rescue, right. So essentially what this daemon has to do is he has to acquire the information of the velocity of every gas molecule at every moment, right. So he is storing that information, and since we know that this process is irreversible, there has to be some entropy generated, right. So there is no process in which entropy is reduced, and you can see that in this case the entropy is going down, right. So the way we basically solve this paradox is, so decrease in entropy due to sorting, right. So basically what he is doing is he is sorting these gas molecules, the hotter ones are separated and the colder ones are like on a different container. So this is exactly balanced by the increase in entropy of information. Okay. So he might be reducing the entropy of this system, but he is also creating an equal amount of entropy in gathering that information about all those gas molecules, all right. So on average, on net, the entropy, the change in such that the change in entropy for this process still is greater than or equal to 0 according to the second law of thermodynamics, right. So I will not really go into detail, but this is where the entropy of information comes out to be very important. Okay. All right. So basically what we will do is we will now go back to the concepts of thermodynamics that we had been doing. So now that we have understood the concept of entropy, okay, so let us start a new concept which is known as thermodynamic potentials. So remember we have been talking about the state of function, right. So this is state variables, right. So like I mentioned in the Carnot engine, the internal energy is a function of a state, right. No matter what you do to your system, if you come back to the same point, you still end up with the same internal energy, right. So in that case, internal energy is known as a state function of that particular process. All right. So basically, okay. So basically, what I am saying is, so the state function remains conserved over a cyclic process. All right. And one such example I just mentioned is example internal energy, right. Internal energy, which we denote by quantity U. All right. And when we basically start from an equilibrium state and say go to another equilibrium state, whether we do that process reversibly or irreversibly, the change in internal energy will always be constant, right. So that will always be U2 minus U1, and if we are doing a cyclic process, whether it is done reversibly or irreversibly, the change in internal energy will always be 0. All right. So and we also saw from first law, right. So we can write our the differential in this internal energy as TdS minus PdV. All right. And here we can see that the natural variables in this equation of the internal energy are entropy and volume, right. So in some sense what I am saying is, in this setup, the internal energy as a function is a function of two variables, which are entropy and volume, right. So those are the natural independent variables in the problem, right. But we usually encounter situations where we are not able to measure the quantity entropy, or we are just not interested in quantity like volume, right. So the question that we are posing is, okay, so sometimes S and V are not convenient variables, and we want to get the same information about the state of the system, not using these variables, but using different variables, right. So basically what we want to do is, so basically can we construct new functions of states, basically new functions of state, right. So we very clearly know that internal energy is one of them, but can we come up with new functions of states which don't have to be the functions of S and V alone, right. So can we derive a quantity equivalent to the internal energy, which is whose natural variables are different thermodynamic variables, all right. And these new functions of states, right, these new functions of states, they are known as thermodynamic potentials. And let us see how do we construct them, right. Okay. So the technique to do that is known as Legendre transformations. So Legendre transformations. Okay. So say that I have a function f of x and y, right. Okay, so even before that, say I have a function which is just a function of one variable, say just f of x, right, and I can represent this function f of x as follows. So x is on the x axis and f of x is the function, and what I will do is, so I'll input a quantity x and I'll get the output, right. So for every value of x, there is a value of f of x, right, and this function has some form, right. So I can like join it or something. So this function has a certain form, for example, right. But say rather than okay, so that is one way to express a function, but there is another way which is as follows. So, say rather than getting the value of that function at that particular point, I can also think about it as the slope of that function at that particular point, right. So, say I calculate the slope of this function at that particular x, okay. So, slope, right. Okay. So, that also gives you the unique value of that function. Of course, the function can go up and down and still remain the same when we talk about its derivative, right. So, what I am saying is I can also express this as a new function g of x, where g is del f by del x, right. So, there is another way I can get the same information, but now thinking about the slopes or the derivatives of this function at any given point x, all right. And of course, like I said, this function can go up and down and g can still be same, but we can always set some reference value so that it matches with the old function, all right. So, that is the main underlying concept of this, okay. So, now let us go back to a two variable problem as we have been discussing. So, say we have a function. So, say for a function f, which is a function of x and y, right, we can write its differential as follows. So, we can write its differential as df equals del f by del x times dx, right, plus del f by del y times dy, okay. And let us call this del f by del x as u of x y dx plus v of x y dy, right, and these are two new functions, okay. And now say I want to convert, okay. So, so we want to convert f of x y to a new function which is g of u and y, right. And what is u? U is basically the derivative of partial derivative of that function with respect to one variable, which is x, right. In the same spirit as we were doing before when we only had one variable, okay. So, the trick to do that is we define a new function g, which is f, the old function minus the product of variable which we want to replace times the product of times the variable which we want to replace it with, right. So, what I am saying is we are replacing x with u. So, you just subtract u times x from that, okay. And this sign can change according to the sign here, right. So, for example, we might have a function which is del f by del x dx minus del f by del y dy, right. So, for some reason there can be a minus sign, in which case we can put a plus here, okay. So, basically the trick is to basically add or subtract a function, a quantity which is product of the variable, the new variable and the old variable, okay. And very easily you can check, in this case this dg becomes df minus d of ux, and if you like just put these things back. So, this is basically u dx from this. So, df is u dx plus v dy minus u dx minus x du, and you can see these two terms cancel out and we end up with v dy minus x du, and this is your dg. And here clearly you can see that your g is a function of two natural variables. Sorry, so this should be u, okay, and maybe I can write it like this. So, this basically can be written as minus x du plus v dy, and you can see that now this is g is a function of new natural variables which are u and y, right. So, this is the technique that we use to create new functions out of an existing function, all right. And also here you can see that your x, the x variable becomes, in terms of new function, is partial derivative of this new function g with respect to u with a negative sign at constant y, and your this variable v is partial derivative of g with respect to y at constant U. Okay. So by remembering this trick, now what we will do is we will construct new thermodynamic variables or thermodynamic potentials using the internal energy as the original function. Okay. All right. So the one important thermodynamic variable or thermodynamic potential that I am sure all of you have used is known as enthalpy, and this is denoted by a symbol H, right. And what is enthalpy? So remember our internal energy was a function of S and V, right. So say for some reason, say for some experimental reasons, so we do not have, so remember, so our U was a function of S and V. Say for some reason experimentalists do not have the access to entropy, or they do not have the access to volume. Say for some reason we want a new function, say H, which is a function of S and P, because say we do not have access to volume. Volume is not a natural variable, but the pressure is a natural variable, right. So in this case we can use the same trick as we just discussed of Legendre Legendre transformation, and we can write our H as, so define H as follows. So H is U plus PV, okay, and we are putting a plus sign because there was a minus sign in du, right. So if we do that, so you can very easily see your differential of H becomes du plus d of PV, right. And what is du? This is TdS minus PdV, and this becomes PdV plus VdP, okay. And you can see that this is a, okay, and this is your dH, and very easily you can check the temperature becomes partial derivative of enthalpy with respect to entropy at constant pressure, and your volume becomes partial derivative of enthalpy with respect to pressure at constant entropy. All right. So this is how we can convert internal energy into what is known as enthalpy. All right. And we can define another thermodynamic variable which is also very useful. It is known as Helmholtz function. Okay. So this new thermodynamic potential is known as Helmholtz function, or also it is called Helmholtz free energy. Okay. And this is typically denoted by a function f, which is now a function of variables temperature and volume. Okay. And again what we are doing is we are replacing the entropy S with T, right, V remains same. So therefore we define this free energy or Helmholtz free energy as U minus Ts, right. We do this Legendre transformation, and here also you can see your dF becomes du minus d of Ts, and if we replace du as Tds minus Pdv, and this becomes minus Tds minus SdT, right. So Tds minus Pdv minus Tds minus SdT, and these two terms cancel out, and this is minus SdT minus Pdv, right. And clearly you can see in this case, okay. So in this case these thermodynamic variables like entropy can be defined in terms of this new thermodynamic potential. So this is del F by del T at constant volume, del F by del T at constant volume, and your pressure becomes negative of del F by del V at constant temperature, and this is and this F is known as Helmholtz function. Okay. And the last one is known as Gibbs function. Okay. Gibbs function, and this is also known as free energy. Okay, Gibbs free energy, and this is typically denoted by a symbol G, and here the G is a function of variables T and P, right. and now we can compare this with our old free energy, which is the Helmholtz free energy, which was the function of T and V, and here it is a function of T and P. So, we are replacing V with P, right. So, therefore, we represent our new function G as the Helmholtz function plus PV, right. And you can also see, since Helmholtz function is already U minus Ts, so this is also equal to U minus Ts plus PV, right. And if we take the differential of this, so we can check dg equals df plus pdv plus vdp, and we already know df is minus sdt minus pdv, right, minus sdt minus pdv plus pdv plus vdp, and these two terms cancel out and we end up with minus sdt plus vdp, okay, and this is your dg. And again, these variables like entropy can be expressed in terms of this new function as partial derivative of g with respect to T at constant pressure, and volume becomes partial derivative of g with respect to P at constant temperature. Okay. So, this is how we can construct new thermodynamic potentials from a state of function, which is the internal energy, all right. So, now let us go through the physical meanings of these potentials, right. So, why do we need to invent them? Okay. So, let us see what do they mean physically, right. Okay. So, let us go to enthalpy first, right. Enthalpy, which we denoted by symbol H, right. And the way we defined enthalpy was H equals U plus PV, right. And the logic behind this is, so in some cases the chemical reactions or thermodynamic processes, they happen at some constant pressure, right. And what happens is the volume can change abruptly, right. So, say you are doing a chemical reaction in a test tube, and since we are like, there is a constant atmospheric pressure getting exerted on that system, and due to chemical reactions the volume can change immediately, right. And in which case it is sometimes not easy, and it is sometimes not even useful to keep track of internal energy of the system, right. But we are interested in completely different quantity. Okay. So, what I am saying is, say we have a system. So, say there is some thermodynamic process in which the happening at, okay. So, the processes happening at constant pressure, right. And say in that process, okay, I am taking an extreme example. So, we had a system which had internal energy U and volume V, right. And say after some time, okay, this system completely disappeared, right. So, this system completely disappeared, okay. In which case what will be the change in energy in this case, right. So, remember the volume is completely disappearing, okay. So, therefore, so the amount of energy which will be released, okay. So, let us say in this case I am asking a question, what will be the change in energy? Change in energy, okay, when you have a system which has an internal energy U, volume V, and it just completely disappears, right. So, remember this system is being acted upon by some pressure P, which is constant from all directions, right. So, therefore, the amount of energy that will be released, that will not only be U, okay. So, the amount of energy released, which is now the enthalpy, that will be U plus another quantity, which is V times P times V, right. Because since atmospheric pressure P is like working for you, right. So, it is filling that void that was created once this system was like once this system basically vanished, right. So, therefore, the energy released will not only be U, but U plus PV, because the atmosphere is also doing work on you, for you, right. So, therefore, this will be the new energy, where PV is basically equal to work done by, let us call it environment to fill the volume V, right, and that will be P, which is constant, times the change in volume, which is V, right, provided the pressure is constant. Okay. So, therefore, you can see that when we are when the system undergoes changes in volume and it is not easy to keep track of internal energy, we can always create a new thermodynamic potential, which is enthalpy, and it is always convenient to work with it. Okay. So, let us take the second one, right. So, what is Helmholtz function? Helmholtz. Okay. All right, and the motivation to basically construct such a function is follows. So, sometimes we are not interested in energies, we are interested in what is the amount of work extracted, right, from a certain process, right, and this is most useful for processes happening at constant temperature, right. And we will again take the same example. So, say we have a system which had an internal energy U and some entropy S, right, and say there is a thermodynamic process where this system just completely disappeared, okay, it just vanished. Okay. So, the question that we are asking is what will be the so, what will be the work extracted in this case, right. So, the work which is now denoted by Helmholtz free energy F is not just U, right. You might imagine that all this internal energy can be converted into work, since this process is happening at constant temperature and this entropy cannot really disappear, right. So, entropy can never decrease in any thermodynamic process. So, there is some heat, right. So, some heat dissipated corresponding to that entropy, which is given by T times S. Okay. So, there is this heat. So, heat dissipated, which is Ts, right. So, therefore, the work extracted is U minus Ts to compensate for that heat which gets dissipated due to the entropy of the system, which is S, right. So, that is how this Helmholtz function becomes useful, right. So, along the similar lines we can also conceptualize the meaning of Gibbs function or Gibbs free energy, right. And again this is valid or this is useful when processes happening at constant temperature and pressure, right. So, again, so you have this system which has an internal energy U, it has an entropy S and volume V, right, and again say it disappears completely. Okay. And again we are trying to ask the question, what is the amount of work which we can extract, right. So, in this case, so the work done which is G is you might imagine this is U, but we saw that some heat is dissipated because of this entropy S when that process is happening at constant temperature. So, we subtract minus Ts from it, and also when the system disappears, the atmosphere basically does work for you, right. So, atmosphere, so the environment does work for us, right, and that is PV, but there is a heat also which gets dissipated, and heat dissipated is Ts, right. So, therefore, we subtract that minus Ts and add that PV, right. So, therefore, this is the net work that we can extract from a system which has an internal energy S U, and once it disappears and say that process is happening at a constant pressure and a constant temperature. Okay. So, this is how these variables they become important, right. So, for processes which are happening at different conditions where the different natural variables are in play, we can construct new thermodynamic potentials to understand the processes. Okay. Okay, and there is other reason why these thermodynamic potentials are useful, especially the Helmholtz free energy and the Gibbs free energy. Okay. So let us see how that is the case, right. So basically the concept of free energy. Okay. And why this is important, because the Gibbs free energy and Helmholtz free energy decide the direction in which a thermodynamic process thermodynamic process evolves, right. So, we already saw that that there is a quantity which is called entropy, and the sign of the change of that quantity in a system can tell us whether that process is feasible or not feasible, right. But we will now very quickly see that there is another quantity which is called this Gibbs or Helmholtz free energy, which also provide us with the same information, right. And let us see how do we do that. Okay. So, let us say we have a system. Okay. We have a system. So, this is our system which is at certain temperature T, and say it is in contact with a reservoir which is at temperature Tr. Okay. So these systems are free to, so this system is free to exchange heat with its reservoir, right. So, since it is in contact with reservoir, heat can flow in and out of this system. So, system can exchange energy with each other, right. So now let us say this process is happening, and what will be the change in entropy of the universe corresponding to this process, right. So, total change in entropy of the universe, and that will be ds of universe, right, and that basically will be just sum of the change in entropy of the system plus change in entropy of the, let us call reservoir, and let us call this equation number 1. Okay. So this is what will happen. So, the change in entropy of the universe will be basically sum of change in entropy of the system and change in entropy of the reservoir, right. So, now let us apply first law to the system, right. So, from first law, okay, so the change in internal energy of the system is basically given by TdS minus PdV for the system, right. And say this process is happening at fixed volume, say the walls of this container of this system, they are rigid, they do not really change the volume. So, at fixed volume, right. So, we can see that your du just becomes TdS, or we can define our ds to be the change in internal energy divided by the temperature of the system, right. And now, if we apply the first law to the reservoir, and say reservoir also is kept at a constant volume, it also does not change its volume. So, and for the reservoir, so we can see that the change in entropy, which is DSR, will be given by DUR, which is the change in internal energy of the reservoir divided by TR, where TR is the temperature of the reservoir, right. And now, we know that in case of thermodynamic equilibrium, say the system has achieved thermodynamic equilibrium with the reservoir. So, in equilibrium, the change in internal energy will be as follows. So, any change in internal energy of the system will exactly be equal to change in internal energy of the reservoir, right. So, that the total so that there is no net change in total energy, right. And similar also the temperatures of these two reservoir and system will also become constant, right, in equilibrium. Okay. So, therefore, we can see that our DSR simply becomes so this is just minus du divided by T, right. And now we can substitute this DSR in equation number 1. So, therefore, so our ds universe, that basically becomes ds minus du by T. Okay. So, ds minus du by T. Okay. So, we have expressed the change in entropy of the universe in terms of the parameters that are related to the system, right, and I can just write this as follows. So, this is just minus 1 by T of du minus TdS. Okay. And what is this quantity, right? So, remember in Helmholtz function. So, since the Helmholtz function or Helmholtz free energy was, we defined it as u minus Ts, and this implies our df is nothing but du minus Tds, provided the process is at constant, happening at constant temperature, which it is because the system is in equilibrium with the reservoir, right, at constant temperature T, which is equal to Tr, right. Okay. All right. So, in short I can write the change in, so when this process is happening, the change in entropy of the universe can simply be written as minus df, right. So, minus df divided by T. Okay. And now let us apply second law, right. So, according to second law, we know that whatever happens, the entropy of the universe can never be negative, right. So, ds universe has to be greater than 0, has to be, right. And if this is greater than 0, this implies your free energy, the in this case the Helmholtz free energy has to be less than or equal to 0. Okay. So, this is basically you can call it another statement of second law, right. So, this naturally emerges from the second law of thermodynamics. So, all the processes, all the spontaneous processes are possible only when the total energy or total entropy of the universe is either greater than or equal to 0, which also translates to to the condition that the free energy change has to be less than or equal to 0, right. So, this is true for a feasible thermodynamic process. Okay. So, all the allowed thermodynamic processes are those where there is a decrease in the free energy of that particular process. Okay. So, in the last okay, so this was all about the thermodynamic potentials, how we can convert the internal energy, which is a function of a state, into other variables which are also function of states, which we defined as thermodynamic potentials, and they are useful if the processes are happening at for different natural variables. Okay. So, towards the end I would like to say one last thing about this entropy, which is basically we will just look at the first law of thermodynamics through the lens of Clausius's inequality. Okay. So, first law and Clausius inequality. Okay. So, if you remember, So, in Clausius inequality, so what we did was, so we created our system at between two states. So, the transition from state 1 to state 2 was an irreversible process, but from state 2 to state 1 was a reversible process, right. So, this is irreversible, irreversible, and this is reversible, right. And we saw from Clausius so we saw that from this Clausius inequality, the change in entropy, which is S2 minus S1 along the irreversible path, has to be greater than or equal to the integral from 1 to 2 of dq irreversible divided by t, right. And this basically translates to the condition that T times ds has to be greater than or equal to dq irreversible if this process is happening at a constant temperature, right. So, this is for an irreversible okay. So, this is what this is true for an irreversible process, but remember for a reversible process. So, TDS okay, actually I should be careful. So, for irreversible process TDS is always greater than dq irreversible, but for a reversible process dq, so this is reversible, right. So, let me, so this is reversible for reversible process. Okay. But we also know, okay, but we also know for an irreversible process, what is the amount of work done, right. So, the change in work which is irreversible is greater than minus PdV, but on the other hand the work, change in work for a reversible process is exactly equal to PdV, right. So, it is like saying if we are undergoing an irreversible process, the amount of work done is not just P times the change in volume, but this we should also account for any losses due to friction or sound or whatever processes which cause irreversibility in the system, right. So, you have to always do an extra work when the process is happening irreversibly, right. And what this statement tells us is that when we do that extra work, right, so that gets converted into the excess entropy that is generated through the Clausius inequality due to virtue of moving between two states in a irreversible manner, right. So, what I want to say is, so for okay, so for both, okay, so let us now apply first law to this, right. So, from first law, the change in internal energy for a reversible process is dW reversible plus dQ irreversible, right. And also the change in internal energy if that process is happening irreversibly, that is irreversible plus dQ irreversible, right. So, whether the process, sorry, so this should be reversible. So, whether the process is happening reversibly or irreversibly, we are basically just transitioning from one equilibrium state to another equilibrium state. So, since u is a function of state, the change in internal energy has to be same whether that process is happening reversibly and irreversibly, right. And for the left hand side to be equal to each other, right, for these two processes done either reversibly or irreversibly, any excess of work done has to be balanced by the excess and the heat released due to excess entropy, all right. So, first law remains valid, right, and essentially, okay, so excess work done during an irreversible process that is exactly equal to heat dissipation due to excess entropy change. Okay. So, whatever entropy is getting produced, that accounts for the heat dissipated during the excess work done to undergo an irreversible process. Okay. So, this is actually very important condition. Okay. So, yeah, thank you so much. I will see you in the next class.